Hi, my name is Christopher Cal. I'm going into my second year for robotics master's program at Penn. And I just want to talk about this, my first exciting week working on the F-110 racing car. So let me just show you what it looks like first. It's almost completed, but not entirely done. But this is the F-110 racing car right here. And basically it's using a Traxxas chassis on the bottom, the Traxxas Rally 4-wheel drive. And then on top of this, we have a NVIDIA Jetson TX2, which is, this is the TX2 here, and here's a carrier board on top. The TX2 is about $600, my education discount is about $300. The Orbi board is about $200, which allows you to plug in HDMI and stuff, and you actually see it on the monitor, which is super cool. Over here is a power board, which was soldered by members of the F-110 team. But essentially what a power board does is it takes in power from DC, from a battery. In this case, I'm doing it from a wall plug, and converts from anywhere from 9 to 36 volts to 12 volts output. And the reason why you need 12 volts is so they have a steady stream to the Orbi carrier and the NVIDIA Jetson board. On a normal battery, it's supposed to last about 6 hours for the computer. Although sometimes it's 3, sometimes it's more, so it's better to just plug it into the wall for debugging purposes. So I wanted to just talk a little bit about some of the things that I've come across, some of the challenges. You know, I've literally prepared this entire list of things to talk about just because it's very overwhelming sometimes to think about all the things that F-110 is. But before we get to that, let me just show you a little bit about what F-110 is and why I got interested in this. And right now, by the way, is mid-June of 2018. So I'm on campus over the summer and got the opportunity to join the team. So let me pull the browser so I could show you. So F-110, it looks like this. F-110 basically creates these cars. So basically they're these cars like this, and they have all these amazing instructions. It started by MIT in like 2016, but now it has actually expanded into other schools. Penn was basically the second one, and there's so many instructions. The build of materials for everything can cost up to $3,000, but the LiDAR camera is about half of that, and I'm not planning to use one of those. What I was really interested in was I was at an NVIDIA talk where I heard researchers putting a camera, just a single RGB like webcam, kind of like this type of camera, right on top of the car, and basically training a neural net. So the car would be going at constant speed, imagine that, and you just store when you train it, you basically store how many degrees to left or right given the single image. And this was a project called Dave, made about 10 to 15 years ago in the early 2000s. And it's been very successful in the backyard. And NVIDIA sent in with the actual car. They've actually trained it on about 100 hours of driving in all types of weather conditions. And they've actually gotten it to work. And I guess just to show you what I'm talking about is called the NVIDIA Dave 2. So this is their blog about how they've, this guy's hands in the air. And it's just really cool because the fact that you can just use a single RGB camera with nothing else. In their case, I actually talked to one of the researchers there over the phone a couple weeks ago. And they actually did need some more sensors, like sonar in the front in case someone stops. They had a separate sensor for detecting stop signs. So it was not as simple as it may seem, because there are a lot of other things as well. But it's just very interesting for me because as a robotics student focusing on a lot of computer vision and machine learning, it's cool to be able to actually see it implemented in the real world as opposed to just like numbers on a screen when we do like these machine learning projects. So let me show you a little bit about what this simulator is. So basically this is a simulator. It's using the robotics operating system. So before I get there, let me just tell you what's on this NVIDIA tech board. It took me about a week to build. I bought the chassis actually last week when I was home in California and brought it over. I was so excited. And I've had a couple of Traxxas cars before, so I know how much of a pain it can be to fix when it breaks. Because these are called caster blocks and other parts. When these break, it's such a pain to fix because you have to take apart so many pieces here. So that's why I don't want to drive the car yet using any software, because one, I'm just starting to learn ROS. Two, I'm definitely going to make a ton of mistakes. And three, it's going to be a pain to thing. So even here, if you look at this, this is literally this is a simulation, and actually the car crashed after a couple minutes. This is just doing simple wall following using Gazebo. And Gazebo is part of the ROS operating system. It's a simulation tool. And so this is like a Barcelona track, and you're able to basically see around and the car would run by itself. In terms of what I'm doing about ROS is basically this is what it kind of looks like. And again, this is very simple still. This is running the Ubuntu 16.04 LTS, and it's using ROS Kinetic, which is a slightly newer version, not the newest version, but definitely newer than Indigo. And I was very worried about having problems, compatibility issues, because I'm using TX2, and a lot of the tutorials that I show you online were all TX1s, and the TX1 uses 14.04 with Indigo. So I was very worried about that, but it seems to be okay so far. And it's just been so cool. I mean, at least for me, coming from a background with a lot of computer science for undergrad and mostly programming, I haven't learned soldering skills. I don't know how to use laser cutter, and I'm learning all this stuff now. And it's just cool to be able to combine things together and like actually do something cool with computer science outside of just like data structures. So here's an example of what a ROS file structure looks like, because at least for me, it would have been really helpful to actually see it gone through in person. So if you go to desktop, this is my Sims workspace for the simulator. And basically every single one will have these folders in ROS. You'll have a build, you have a develop, install sometimes, you have source. Source is where all your source code goes. So these were all cloned from GitHub. For instance, if we go into one of these, like the F110 simulator, there's all these files inside, and they're arranged in a certain way, which I don't exactly understand yet. And they can be either run with Python or C++. Now, I'm really happy if I can do stuff in Python, because I haven't done much C++. I've done a lot more Python coding, and especially later if I want to do the neural network type of thing, I'll definitely need to probably be writing in Python, probably not C++. So that's just really cool. And you know, if you look at a file like this is all on GitHub, so it's nothing like proprietary. Control.py is like, how do you control the car? Well, and I still don't understand a lot of this, so I hope it doesn't sound like that, but control, it's like, some of it seems a little hard coded. It's like if the angle is greater than that, then do that. The angle is less than that, do that. If the velocity is, you know, this is actually commented out. If the velocity is greater than 2.5, basically you set a maximum velocity of 2.5. There's just a lot of little things in here, and I guess it publishes a message. In ROS, the robotic operating system, each node publishes messages to a topic, and you have listeners. So I guess this would be considered a node, the control node, because it is publishing messages with a velocity and an angle. In many ways, it's kind of like JavaScript, because you're having like a JSON kind of. You're setting a velocity, you're setting an angle, and then you're publishing it, which is kind of like a post request. And then you have someone getting it. This is like the server, and then someone else is doing a GET request. So this is super cool. I want to show you a little bit about how the terminal stuff works. So this is just running the simulator right now. But something I found pretty cool is that ROS, every time when you start it, you have to run something called roscore. So I ran it up here. It's basically like the master server that helps all the different nodes communicate with each other. And you know, this is all stuff I've learned this week. I literally have this stack of papers on my desk. I'm just learning a lot, and sometimes it's overwhelming, and there's a lot of stuff. The F110 website was great because it had a lot of tutorials. So I went through basically almost all of them. Intro to ROS, look at those notes. Intro to the Jetson, which is the NVIDIA board. Robot operating system part 2, using nodes, cat can make. These are a lot of papers that I found pretty interesting. I haven't even read all of them yet. I've only read like one of them, to be honest. And the one I've read is the NVIDIA paper on, they call it, or actually I'll see it right here. It's the end-to-end learning card one, but it's not this one. So I'm not exactly sure where it is right now, but I'll try and find it later just to show you. I mean, you look at the hardware here, it's really interesting because we actually stripped out a lot of things. It's using a brushless system, and it has to have it's best to use brushless because it has 3 prongs, which works with the VESC. A VESC is basically an electronic speed controller. I'm still waiting for mine, and and I'm in no rush because I don't want to drive this anytime soon in case it crashes. But a VESC basically allows the the board, to communicate over USB, probably through a hub or something, because there only has one USB port, in order to get odometry information, tell it things. And it's being used by electric skateboards, like the boosted board. It's used in a lot of new technologies. It's supposed to be a big breakthrough, and I don't really understand why yet, because it seems like the VESC is something that is that we should have had a long time ago. But I guess with the advent of these microcontrollers, it's just made it more possible to send very fine-tuned messages. So we actually took out the receiver, and my friend Jack actually helped me out. He is the same year as me, also going to sub-matriculation. He's helped me out a ton building this. These were 3D printed, and normally they're laser cut, but I was at Penn had an ad lab and got it printed, so that was cool. This I printed at home because I got my little brother a 3D printer, and I printed it last week when I was in California because I was just dying to build this. And so you'll see here, we took out the original electronic speed controller. Don't even have a need for this because the receiver is stripped out. And the way for people to manually override when this is driving is, instead of using something like this, which you can use a computer to control, we will actually use one of those like gaming joypads by Logitech, which is in the lab right now, and use that to build this. The bottom is a really cool plate, which allows me to just turn the car. I mean, if you really just like step back and think about it, like, how cool is it that our car is a computer that is driving a car that is simulating? I mean, it's insane. And I mean, some team members have told me not to run the simulator on TX2, but so far it's working pretty well. I mean, this computer's got 8 gigs of memory. It's pretty powerful, and it has CUDA cores, and honestly, I think it's probably more powerful than my MacBook Pro, if not around the same. So I think it's pretty damn impressive. So this is the simulator. Let me just minimize this. Basically show you this. It's funny because when the car crashed, it actually keeps going like that. But let me put the camera down and just talk you through kind of some of my thoughts, some of the challenges that I've seen. It's about 12 minutes into the video, but there's a lot I want to talk about. So let me just make sure it's going to correctly. Yeah. So I just want to talk a bit about how excited I've been this past week. I mean, literally a week ago, or 2 weeks ago maybe, I was in California just driving normal RC cars, Traxxas models, which I've had for a long time. And this summer I was planning to continue doing my drone photography with Philly by Drone, but I was feeling very little bored and little empty inside because I've been taking so many robotics classes and I wasn't applying it in any way. And I know that this next year I'll be taking about 4 master's classes a semester, where normally students take 2 or 3, plus I have some undergrad classes. So it's going to be a ton of work. And so I wanted to get a head start. I debated about maybe doing some research over the summer. Maybe some research just to get a course credit for the engineering thesis for my undergrad credit. And I was lucky enough to find out F110th because I saw it in February at a conference at Penn, an industry symposium, where I also met those NVIDIA researchers doing the self-driving car. And I just thought it was really cool because it's a cool way to apply a lot of the things. The F110th team, many people left for the summer or have graduated, so the team's kind of being built up from scratch again. Of course, there's a lot of resources. And so I've been involved. I've been at the M Lab with Professor Rahul Mangaram, Jack Harkins, who sits next to me. He's been there a couple weeks now, and I just started. And so I might even be helping to TA a course that Professor Mangaram is teaching, which is going to be super cool. But anyways, let me talk to you a little bit about what I've done so far and what the next steps are. So originally, I already felt overwhelmed thinking about the hardware that would have to be completed, because I'd have to get the car. I didn't know what the power board was, especially if I was in California. I didn't even know if I would be able to get my hands on one of those power boards. So I was lucky enough to be at Penn. I mean, it's literally right across the street. Talk about location, to be able to just go there. I could go there right now on a weekend even. It's just so, I mean, having access to a lab is really such a great resource, and especially the people in the lab. So I built the hardware. I had the car. I had the 3D printer. I mean, I had to buy even these pieces online. And maybe it looks easy once it's completed, but it was really a pain because you see these standoff plates? Each of these standoffs is like $4 online for the McMaster car. like they're not cheap, but they have to be specific heights, you can mount it perfectly. So I bit the bullet and spent $100 just on those and like M3 screws. I mean, it's really crazy if you think about it. A LiDAR camera can only be $1,500, but I didn't want to spend that much, and I also wanted to try the convolutional neural network approach. People can mount a Z camera on front, which is a depth camera. I mean, people can go crazy with this. But basically, the hardware's been done now. After a while, I had to flash the Jetson pack. I mean, I did not know what it even meant to flash a computer, and I'm studying computer science. So when I had to reflash it the second time, I didn't realize it would delete all my files. Luckily, I didn't have many files besides installing ROS, so I did that over again. I mean, this past week, I literally got here on Tuesday, now Saturday, June 16th, and I've slept at 1 or 2 a.m. multiple nights just because it's like midnight and I want to fix something, and then something breaks, like the flash I find out didn't install ROS correctly, and then so I just didn't want to go to sleep until I finished it, which is kind of funny. But it also shows that it's pretty interesting to me. So a couple things that I'm currently working on after getting the hardware and starting to get the simulation. The simulation, by the way, took like 5 hours just to figure that out because we had to go through all these steps. I mean, I didn't even know what the ROS structure looks like. I have to do roscore, ROS launch, all these things. I was getting an error because it was missing some Barcelona track. And then I realized that the instructions were outdated. The instructions were outdated because I actually had to pull from GitHub the race car simulation from the MLab UPenn, not the MIT version, because the UPenn version is slightly updated with some more worlds. Which, by the way, is really cool that you can just input a world into it and tell it how to go. I mean, when I showed you that simulation earlier, the fact that you can just run that, it's going to be really powerful because for a course where students are implementing algorithms for the first time, I don't think that we want to be driving the car down hallways, especially when these cars with LiPo batteries can go up to like 60 or 70 miles per hour. Something goes wrong, it even breaks someone's foot, which is crazy. So, I mean, in terms of simulation, like there's so many things that I don't know. And I'll just name drop all the things I don't know because there's like so many things that it's like almost overwhelming sometimes. Let me make sure it's still recording. All right. So some of the things that are really confusing to me, first of all, when I run the simulation, what are all the nodes? I mean, how many nodes are even going on? I have no idea. There's like a control for the car. I know the ESC electronic speed controller might have one for the VESC. I know that even turning and steering and maybe the laser scanner sending stuff, and there's like all these topics that are being sent. It's like crazy. When you do the graph, you get a full screen with like 20 or 30 different nodes. So I really need to spend time to sit down, visualize it all, see all the topics. I mean, it's crazy. And then you can echo each of them to see all the data that's being sent, which is just crazy. And that's just a simple part. I mean, that's not even the car running yet. That's just the software running together, all the nodes communicating with each other. And then once I have that, I want to understand all the Python files, like how do you write code, even to just make the car go forward. Because it seems kind of simple normally when you're in Java, just in the virtual world, you could do like carol.move, if you're familiar with Carol, the things for that Carnegie Mellon for learning I did in high school. But in this case, to make the car go forward, well, here's what you have to do. You have to have the control.py, which is constantly looping. You have to set the velocity at 1, but you can't just say 1 because sometimes it might get faster or slower, so you have to set if statements. Like if it gets greater than 1, keep it at 1. If it goes less than 1, keep it at 1. That's the simple part. Then you have to send over some topic, which is unknown. I don't know what it will be called, but someone's going to be listening on the other side. It's probably going to be like the VESC maybe. So the VESC then listen to say, oh, velocity is 1. Okay, I'm getting this message. Let's tell the robot to move. So the VESC, I guess, has its own node, and it's open source, so they figured all that out. It'll then tell the actual hardware. To then spin this motor some certain times, which you have to calibrate by measuring to go at a velocity of 1, whatever unit that is. And then it just loops. And I guess but there's so many parts going on. Then you have LiDAR sensors constantly listening. And if the LiDAR detects something 1 foot away, then it tells it to stop, but then it's telling it to move before it gets, I'm just trying to process everything that's going on. And then it gets a little more confusing because that's just simply moving. But obviously to make a self-driving car, you're gonna have to have pretty smart brains. It's gonna need to have control and planning algorithms, which I've never taken a class in before. I've only taken machine learning, computer vision, and machine perception, which are more on the computer vision side. So, I mean, I don't know any of these. There's something called PID, which I haven't learned about before. It's kind of like when a car turns a corner, you don't want it to just like go on the inside and make a wide lane. You want to go on the outside and cut a short lane in. I mean, there's all these things, and all of F1 10th racing so far has just been individual trials. So they'll have a track set up, and the car will move around. I'll show you what the track looks like, just because I think it's important to see. The track, here's an image of a track. So if you look here, this was like one of the tracks on one of the international competitions. It's like kind of a bird's eye view type. Looks kind of small, but it's actually pretty tall, and they use these air duct tubes in the bottom, stacked 2 on top of each other, because if you only put one, then it's not going to, if you only put one, then the LiDAR might not see it sometimes if it's too close. So, I mean, there's all that stuff. I'm going to be figuring out this week how the simulator works. I need to improve it, need it to be realistic. Hopefully I can write my own path planning algorithm. That's the plan. And then in a couple weeks, once I have the hang of how to control the robot and how to make it move, I'll then start installing a sensor on, probably this RGB camera right here. Although I heard the frame of view isn't wide enough, so I may be using a different camera. In my opinion, it should be high resolution, but a lot of the ones I've seen, people use really cheap cameras. But to me, I feel like it's really important to have a really good camera on it, because that's like, if it's the only sensor the car's using, I personally feel like, especially coming from a photography and drone photography background, I feel like it's important to have a pretty clear camera, but you obviously can't be using 4K, because a 4K camera is not going to process. It's like way too big of a file. So it'll have to be downsized eventually anyways, but to have a wide frame of view and stuff, I think is very important. So neural network will be a huge thing, especially because when I worked on neural networks last, I used code that was already existing and improved on it slightly. So I need to find the open source code, and then how do I train it? I'm not really sure. I guess I'll be probably using that little joystick thing, the Logitech, to train it, and I'll just a really good tip I got from Ben from NVIDIA was just start something very simple, like going around the table. So I might just train the car and just spend like an hour driving it around the table, and I don't know if I should do it in both directions or just one, because I might confuse the car. Probably one direction, going constant speed of probably like 1 mile per hour. It has to be constant, because if it speeds up, then the turning orientation actually changes things up. So it'll kind of just go around the car or around the table. And I guess I would just load all those in. All the files have to be downsized. When I do this, I need some script that's literally saving all the data. Every single image frame is going to be saved. And you know how big images can be. If we're talking about 24 frames per second, or maybe it'll be slower because maybe we don't need every frame. Even if it's 2 or 3 frames per second over an hour, I mean, that's literally like 10,000 images. 10,000 images. Each one needs to store like the angle is turning, which I guess would be stored through the controller. I mean, it's not easy stuff. And even just figuring out the controller, like you control, okay, but how does that correlate to how many angles the car is turning? Because we don't want it to be dependent on the specific controller. We want it to be dependent on the actual angle that the wheel's turning. And then that's going to something called some Ackerman steering, which I also don't know about. So the people in the lab are like, there's so many textbooks laying around, and like Jack was just like reading one, like, oh yeah, like professor told me to read this control book, so I'm reading it now. There's a lot of stuff, but it'll be good because as a computer programmer, a computer scientist, I have not done much on the hardware side, and it's important to, I mean, if I'm studying robotics, I feel like it would be a shame not to have done anything with an actual robot during my 2 years of master's program. Normally master's is actually 2 years, but I'm taking 1 extra year above my 4 years of undergrad because I still matriculated. So those are mainly the things I wanted to talk about. I'm planning to record this each weekend just so for myself, for learning purposes, and later on if I decide to upload these as well for people to see and kind of learn from. Just to conclude, let me just show you a little bit more of the car. So, because I know it is really cool. Just so in case anyone wanted a pretty clear view of it. I mean, this is the car, it's super cool. This is the board, which Jack soldered, and I was just sitting next to him watching. I mean, I've really learned a lot. There's a brushless motor, there's the shocks, which actually need caps on them to compress the springs because the car's heavier now, so the car sags more. And yeah, I mean, it's gonna be really cool. and I have about 2 months before school starts, so that's about 8 or 9 weeks to really get this up to speed. And eventually I might be TAing the course, might get a course credit, and it'll be cool. It'll definitely be cool. This is stuff that I definitely would not know how to do in undergrad, and yeah, I mean, doing a master's really exposes me to a lot of new things. So just be humble and we'll learn a lot. Thank you.